We all know the best MC, it's M to the B, it's M to the B, it's M, 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 M to the B, it's M to the B, it's M to the B, bang.
In the last lecture, we defined an R-module homomorphism and R-module isomorphism because we wanted to ask the question of when two f bracket x modules are isomorphic. So in this lecture, I want to say more about R-module homomorphisms and isomorphisms. And let me start by recalling the definition from last time. So R is a ring, M and N are R modules. A map phi from M to N is an R-module homomorphism if it's a homomorphism of abelian groups and it behaves nicely with respect to the action of R on M and on N, by which I mean phi of R dot X equals R dot phi of X. So R is an element in the ring, X is in M, and phi of X is in N. So the action of R on M and on N, these actions are compatible with each other in exactly this way. An R-module homomorphism is an isomorphism if it is also injective and surjective. Okay, now that we have a homomorphism, here it's an R-module homomorphism, you should think, how does this compare to group homomorphisms and ring homomorphisms? Well, just like in those settings, we can define the kernel and the image. So if you have a map from M to N that is an R-module homomorphism, the kernel is the set of all things in M that map to the 0 element of N. And the image, which we'll denote with im of phi, or Dummett and Foote generally use phi of M, is the set of all things in N that get mapped to by some element in X. So just take a second and look and see that, I mean, this just is the kernel of phi as a group homomorphism. It's the same set of elements, right? There's no like action of R showing up anywhere here. So the kernel and the image are defined just as they are for a group homomorphism. Okay, now here's another definition. It's going to be helpful for us not to just think of these homomorphisms one at a time, but the set of all of them. So that's going to be something that'll be a big focus in the next lecture. So let's say that M and N are R modules. We're going to define hom sub R Mn to be the set of all R module homomorphisms phi from M to N. So the R here is indicating that we're thinking of R module homomorphisms that go from M to N. All right, so exercise 1 in section 10.2 says that you can use the submodule criterion to show that kernel of phi is an R submodule of M, and the image of phi is an R submodule of N. So you really should do this exercise. For one thing, it's a nice application of this submodule criterion that we proved at the beginning of this lecture. But how does this argument go? Well, what do you need in order to be an R submodule? You need to be a subgroup. And we know that the kernel and the image, the kernel is a subgroup of M, and that the image is a subgroup of N. But you also need that the kernel, that this subset is closed under the action of ring elements. So this is really common here. So some of these statements look just like statements we've proved for groups, rings, ideals. And often what happens is you have the corresponding argument that works for groups, and now you just need to check one additional thing about the action of your ring R on your sets. So you have to check everything works as it did for groups, plus something additional about the action of R on your elements. So you should do this exercise, and I'll say this is one of several exercises that are really similar to analogous results for groups, rings, ideals. So what do I have in mind? I'll point out section 10.1, exercises 6 and 7, and then section 10.2, exercise 2. Okay, so I'll pause and erase, and then we'll talk about examples of R-module homomorphisms. The first big example we would like to look at is the case where R is a ring and you take M equal R to be an R module. So R is a module over itself. You should think of it as a left module over itself in the case that R is not commutative. But if R is commutative, you can just say that, okay, R is an R module. All right. So in this case, we can compare two different kinds of homomorphisms. We can compare the ring homomorphisms, phi from R to itself, and then we can compare the R module homomorphisms, psi from R to itself. And the thing that I want to emphasize is that these are not the same. So what are the things that need to be true in each case? What needs to be true for a ring homomorphism? We need to have phi of x plus y equals phi of x plus phi of y. And we need phi of x times y to be phi of x times phi of y. What about when you think of R as a module over itself? What has to be true for an R module homomorphism? Psi of x plus y is psi of x plus psi of y. Hey, that's the same. Great. But psi of x dot y, where now this is representing the action of x on the module element y. This is, for this to be an R module homomorphism, this has to be the action of x on the module element psi of y. So it has to be x dot psi of y. Okay, these conditions don't look the same. These are not the same condition. So let's give some examples. So let's take R equals z. So we can compare ring homomorphisms from z to z and R module homomorphisms. Sorry, let's say z module homomorphisms from z to z. So let's take psi, the function that goes from z to z, defined by psi of x equals 2x. This is a z module homomorphism for sure. I mean, it's a homomorphism of abelian groups. It's a homomorphism from z to z. But it's definitely not a ring homomorphism because it doesn't behave nicely with respect to the multiplication in the ring. Like psi of x times y is 2 times xy, right? You take the element in z, x times y, and you send it to 2 times xy. But if x and y are not 0, that's just not equal to 2x times 2y, which is psi of x times psi of y. So we're seeing that this function is a homomorphism of abelian groups. It is a z module homomorphism, but it's not a ring homomorphism. Let's give a different kind of example. Let's say R is f bracket x, and we can define this function phi, which takes f bracket x to itself by taking a polynomial f of x to f of x squared. So every time you see the variable x, you'll just substitute in x squared. This is a ring homomorphism. And you should check this. You should really check that this is true by checking each of these properties. But this is not an f bracket x module homomorphism. Why not? Well, x squared is phi of x, which is phi of x dot 1. When you think of f of x being a module over itself, the action of elements of your ring on elements of your module is just multiplication. So this is phi of x dot 1. X dot 1 is x. But if this were going to be an f bracket x module homomorphism, this would have to be equal to the action of x on the element phi of 1. But phi of 1 is just 1. And the action of x on 1 is just x, because the action of R on this module, where you think of like R as an R module over itself, is just multiplication in the ring. So we're just seeing that x squared is not equal to x. So this map does not satisfy this condition that you need to be an R module homomorphism, but it is a ring homomorphism. So you have to be a little bit careful in comparing R module homomorphisms and ring homomorphisms in this really important case where you think of a ring as a module over itself. Let's continue our discussion of examples of R module homomorphisms. So if R is a field, then what is an R module homomorphism? In each of the last 2 lectures, we've talked about modules over a field being vector spaces over that field. and linear transformations from a vector space, from one vector space to another. So you can check, and you really should check, that the conditions required to be an R-module homomorphism when R is a field are exactly the same conditions that are required to be a linear transformation from one vector space over a field to another. Okay, what about the case where R equals Z? Well, what is the action of a ring element on a module element? So you have some Z module M, which we know is just an abelian group. And what is the action of R in Z on this module element? Well, you just add or subtract that element to itself some number of times. How many times? R times, where if R is a positive integer, exactly what I said is true. If R is 0, you just get 0. And if R is negative, then you're adding the inverse of this element to itself a bunch of times. So, okay, if you have a map phi, and you want to know whether it's a Z module homomorphism, certainly it has to be a homomorphism of abelian groups. So phi of x plus x has to be phi of x plus phi of x. But it has to be more than a homomorphism of abelian groups. You have this second condition, that phi of r dot x has to be r dot phi of x for all x in the module and r in the ring. But if you look at this condition and take r equals 2, x plus x is 2 dot x. So what are we seeing? We're seeing exactly that phi of 2 dot x equals 2 dot phi of x. Phi of x plus phi of x is 2 dot phi of x. So, okay, that's what happens for r equals 2. But either by induction or applying this r times, you can think about it like that, we see that having the group homomorphism condition, that phi of x plus y equals phi of x plus phi of y for all x and y in the module, implies that this phi also behaves nicely with respect to this action of the ring Z on the module M. So, or the module M and the module N. Okay, so what are we seeing? We're seeing that in this case, asking for a function between Z modules to be a Z module homomorphism, well, usually you would think it has to be a homomorphism of abelian groups, and it has to behave nicely with respect to the action of Z on M and N. But what we're seeing is that if you're a homomorphism of abelian groups, then you automatically have this property that the function behaves nicely with respect to the action of Z on the first module and on the second module. So Z module homomorphisms are the same thing as homomorphisms of abelian groups, that the second property follows automatically from the first. Let's talk about one last important example. Let's say R is a ring, I is a two-sided ideal of R. And let's suppose that we have two R modules M and M that are both annihilated by I. So we have this action of R on M, this action of R on N, and annihilated by I remember that that means A dot X equals 0 for all A in I and X in M, or same thing for N. So we've already seen that in this case, M and N are not only R modules, but they're also R mod I modules for this quotient ring R mod I. Where, okay, if that's true, we have to give an action of R mod I on R module elements. So R plus I, the coset of R mod I containing this element little r dot x, is just going to be R dot x, where this is whatever the action of R does to this module element. So we're defining the action of this quotient in terms of the action of the original ring R. All right, so now suppose we have an R module homomorphism phi from M to N. And we claim that it's automatically an R mod I module homomorphism. So, okay, it's certainly a homomorphism of abelian groups. There's nothing to check there. I mean, M and N are the same underlying abelian groups when you think of them as R modules or as R mod I modules. So we just have to check that the fact that phi behaves nicely with respect to the action of R on M and on N means that it also satisfies the required property for this action of R mod I on M and on M. Which action? This one that we just reviewed. So, okay, so what has to be true? If phi is an R module homomorphism, phi of R dot x is R dot phi of x for all R in the ring and x in the module M. But this implies that phi of R plus I dot x, well, what is that? R plus I dot x is R dot x. And then what is phi of R dot x? Well, phi is an R module homomorphism. So this is R dot phi of x. But R dot phi of x is R plus I dot phi of x because of the definition of the action of this quotient ring on our module N. So if phi is an R module homomorphism, we see that it automatically satisfies the thing necessary to be an R mod I module homomorphism. So I'll pause and erase, and we'll give one example of this last, one interesting instance of this last kind of example. Let's discuss an example related to this last observation that we talked about. So let's say A is an abelian group. Let's write it additively where we add elements with the plus symbol instead of times. And P dot X equals 0 for all X in A. So what do I really mean? P times X. I mean X plus X plus X plus X, P times where P is some prime. So I want to emphasize that we're writing the abelian group additively because P is not an element of A. I'm just saying that X plus X plus X, P times, is always equal to 0. All right, so what does that mean? We have this action of Z on A and P dot X, this element of, P dot X, where you think of P as an element of Z and X as an element of this Z module A, is 0. So in fact, if you act on any element of A with any element of the ideal PZ in Z, you get 0. That this module, this Z module, is annihilated by the ideal PZ of Z. So that makes A into a Z mod PZ module. But what is a Z mod PZ module? Z mod PZ is a field. So this is a module over a field. So A is a vector space over the field Z mod PZ. So we have seen that a Z module homomorphism, phi from A to A, which is an element of hom Z A. You can think about it like that, just using this notation we've introduced. This Z module homomorphism satisfies all of the things that need to be satisfied to be a Z mod PZ module homomorphism with the action of Z mod PZ on A that we just were talking about. But this Z module homomorphism is a Z mod PZ module homomorphism. A Z mod PZ module homomorphism is a linear transformation defined over this Z mod PZ. So it's a linear transformation from this vector space A over Z mod PZ to itself. So let's think for a second. A Z module homomorphism that just is a homomorphism of abelian groups. So you have a group homomorphism from A to A. If that is an isomorphism, if that Z module homomorphism is injective and surjective, then it's an automorphism of A. And this is something we studied quite a lot in 206A. This was useful for classifying groups and things like that. And we saw that not only is the set of all automorphisms of A a set, but it has the structure of an abelian group. And okay, so now we have all of the Z module homomorphisms, but we also can just look at the ones that are injective and surjective, the automorphisms. And that has the structure of being a group. But every one of those Z module homomorphisms that is an automorphism gives a Z mod PZ module homomorphism. If this Z module homomorphism is injective and surjective, then this Z mod PZ module homomorphism is also injective and surjective. So you can check that those two conditions are equivalent. So what is the set of these Z mod PZ module homomorphisms, these linear transformations from A to itself that correspond to the automorphisms? Well, they're exactly the ones that are injective and surjective. Those are exactly the linear transformations that are invertible. So what we're seeing is a correspondence between this subset of the Z module homomorphisms that has this additional structure, the automorphisms. This group corresponds to the group of all invertible linear transformations from this vector space to itself, which is denoted GLA. So we've used this GL notation for matrices already, the general linear group of n by n matrices over a field. And more generally, we can talk about the group of all invertible linear transformations from a vector space over a field to itself. And we're going to use this notation GLA for that. So when we talk more about how to go between linear transformations and matrices, you'll see why this is a good choice of notation here, how this matches up with the idea you have of GLN with entries, the group of n by n invertible matrices with entries in a field F.